Assalamualaikum. This is Samiha Tasimoli, ID 2100212241. Welcome to our project video for the Embedded System CEP. In this video, I'll be walking you through our complete design of a standalone handheld Tic Tac Toe gaming device built entirely on the Atmel 89C51 microcontroller and programmed in 8051 assembly language. So our problem was basically to design a low-cost, standalone, handheld tic-tac-toe device targeted at a mass consumer market. It needs to be fun, intuitive to use, and visually appealing, but at the same time, it has to operate under some very real and strict engineering constraints. The device must be built on the legacy 8051 architecture, specifically the Atmel 89C51 microcontroller. It must be programmed entirely in assembly language with no high-level libraries, and it has to meet the tight limits of four things: production cost, power consumption, memory usage, and the input-output pin availability. On top of that, we are in Bangladesh, so every component we chose has to be actually available locally at a price that makes commercial sense. The last constraint ended up shaping a lot of our decisions. So given the problem, we have defined some clear design objectives for ourselves. First was the usability. The game should be immediately understandable to anyone who picks it up, no instruction manual needed. Second was the visual clarity. The player should always be able to tell whose turn it is, what the board looks like, and whether someone has won or if it's a draw at a glance. Third, the full game functionality. There's two game modes. The device should provide two ways of playing the game, either against another human, which is player versus player mode, or against the computer, the player versus AI mode. The mode will be chosen from a special menu at the startup. So there should be clear feedback. The device should provide clear indication of a valid move, an invalid move due to the occupied position, change of turns, winner selection, draw conclusion, or restart. So the fourth objective was resource efficiency. The entire game logic, input-output handling, and AI must fit within the 4 KB of flash and 128 bytes of RAM, the hard limits of the Atmel 89C51. And the fifth objective was low cost and local availability. Every single component in the bill of materials must be sourceable in Bangladesh at a price suitable for mass production. Here we can see the design. So the center of our design is the Atmel 89C51 microcontroller, which is running at 12 megahertz. It manages everything: reading the player input, running the game logic, driving the display, and executing the AI. For input, we have used a 4x4 matrix keypad. So the keys, so the rows and columns are connected to the port 1 pins. And then for output, we have used 16 by 2 character LCD display, which is connected to the port 2 and port 3 pins. So in the next part of our video, we'll go deeper into each part of the design, input output selection, and the hardware implementation. I will walk you through the hardware design of our RetroLogic Tic-Tac-Toe gaming device, specifically why we chose each component and what alternatives we could have considered, and how everything comes together in our Proteus simulation. So the heart of the design is the microcontroller. This is a classic 8051 family microcontroller with 4 KB of flash, 128 bytes of RAM, and we have 32 input-output pins across 4 ports. So port 0, port 1, port 2, port 3 all have 8 pins. For a simple game like Tic-Tac-Toe, 4 KB of flash and 128 bytes of RAM is more than enough. Now our input unit. For our input unit, we have used a 4x4 matrix keypad. This is a calculator style keypad that we can see here. So the key advantage here is the directness. So we can directly press key for the game. So key 1 through key 9 can map 1 to 1 the 9 cells of the tic-tac-toe game. As you can see here, if we press 1, it will put 1 here. So key 1 is cell 1, key 2 is cell 2. Like this, key 9 is cell 9. So another advantage here is the same keyboard can handle the mode selection. As you can see here, 1 is for player versus player. If we press 2, this is for player versus AI. And the key C is to restart the game. So While designing, we also considered individual push buttons, so 9 separate buttons, one per cell. The problem with that is 9 separate button needs 9 microcontroller pins. Also, they take more PCB space and the layout becomes awkward for a handheld device. Another option was to use a joystick, but navigating a cursor to select a cell is significantly slower and it is less intuitive than just pressing a number key directly like here. Another option we had was capacitive touch keys, but even though they look modern and have no moving parts, but they require dedicated touch controller ICs and they're not easily locally available and they're more complex and costly. But our matrix keypad, it only needs 8 pins, so 4 pins for row and 4 pins for column. So these 4 pins, row pins are connected here in pin 1.4 to pin 1.7 and the 4 column pins are connected here from pin 1.0 to pin 1.3. So this is scanned with a simple row column folding routine in assembly, and this is the most cost effective and user friendly option.
Now comes our output unit. For our output unit, we have used a 20 by 4 character LCD, which can handle any output message that we need. So it can show any readable message that we need to show, like whose turn it is, win or draw announcements, invalid move warnings, and mode selection prompts, like we can see here. The LCD connects to the microcontroller in 8-bit mode. The 8 data lines goes to port 3. The RS control line goes to port 2.0 and the enable line goes to port 2.2. So we could use a graphical LCD instead, but even though graphical LCD would give us richer visuals, but it costs significantly more and requires a more complex driver and it consumes more power. So for a simple game like Tic Tac Toe, where we only need to display text messages, a 20 by 4 character LCD is perfectly sufficient and far more practical.
So now we have the clock and the reset circuit. So for the clock circuit, we have a crystal with two 33 picofarad capacitors that are connected to the XL1 and XL2 pins of the microcontroller, which is the pin 18 and 19. So the clock is primarily used for instruction execution. We also generate the delay and the keypad scanning and the LCD interfacing. So we have implemented uh, delay routines using loop instructions. So the timing is derived from the known machine cycle duration, which we would see in our code implementation. Now for the reset circuit, we have a 10 kilo ohm pull-up register to the reset pin with a push button to ground. So if we press the push button for long enough, it will reset the microcontroller. As you can see here, we press it, the microcontroller is reset. So the whole microcontroller runs on 5 volt. The LCD also runs on 5 volt, so our input voltage is 5 volt. So that was our hardware design part. In the next section of our presentation, we'll walk through the game logic and the assembly code implementation. Thank you.
Assalamu alaikum. I am Soumya Alam, ID 2100212339. So right now we will explaining AI logic and assembly code implementations. So we already mentioned in 8051 microcontroller, we are using 4x4 keypad for user in 20x4 LCD for displaying the game mode and messages. LCD indicator driven through a 74HC shift registers visualization feedback. So here are two kind of modes are given, player versus player and player versus AI. AI is designed by competitive by following well-defined priority-based strategy. So there is 8 strategy. There's win move, lock move, frog creation, block frog, center control, and opposite corner and any corner any edges. So this is the 8 priority-based the algorithm that are used for this projects. And this is the memory locations. RAM, mainly we are using some of the instructions at that memory location. So 30 to 38 is C1 to C9. Here I mentions 0 is equal to empty, 1 is equal to X, 2 is equal to 0. So that's why scar P39H current player X1 is equal to X2 is equal to 0. Mode EF3H game mode 0 is equal to PBP and 1 is equal to PBAI. Winner 3BH game result 0 on win 1X wins and 2 0. So LTU 0 to LTU 3 and this is the location of them and LED status plug for visual indications. So this is the key. This is assembly language code AI code moves. This is the level, and here we are using eight priority one by one, and this is the logic that if jump carry this carry is equal to one, then jump to the AI done. So if not going to the priority two, that will find block X. That way, if not, then it will going to find block 0. Then and not, it will going to find block X. And if not, it will take center. If not, take opposite corner. If not, take any corner, or if not, take any edges. Then it will go out the code. Or if any condition is true, that means jump k is equal to 1, then it will directly come into the AI is equal to done. So this is the AI logic in assembly. Right now we are talking about the keypad interfacing. As earlier mentioned, that 4x4 matrix are used for this, and the map is port is 1 to 9. So LCD interfacing, we are using 20 into 4 character LCD display. So this is the player information, so information all are using actually. So LCD initialize, we are initializing the LCD like that 38H. That means 8 bit 2 line 5 into 8 front, and 0CH means display on cursor on. 01H will clear the display. 06H means enter mode cursor incremented, and that's why we are initializing the LCD. So LCD connected by a 74SCH 5 shift register provided quick visual feedback. So LED patterns for player X turn and player 0 AI turn, win and draw. So that's why we are mainly logically and assembly language we are using LCD initializations and taking the AI move in logic in assembly.
Very much so, Rahman Ismail. ID 2100 I will demonstrate how our game is working. So as per our requirements, there are two modes, PvP and PvAI. So to play the each modes, we have to press the corresponding numbers. So let's play PvP. We press 1. First turn will be cross and the second turn will be 0. So let's create a situation where we have drawn. So let's play according to that. Now the turn of 0. So as you can see, we have drawn. So it should say that it's a draw and press C to restart. So we'll play another game. And in this game, we'll play versus AI. So we press 2. Now we will create a situation where we lose. As we are using assembly to program this, we have some limitations. And due to that, our AI is dumb. So to lose, we have to play dumb. So we'll cross and our AI is 0. So I played at 1. Now we'll play it at 3. So let's see where I place. Yeah, I played at 4. So to win, yeah, we will play at 7. So let's just ignore it and we play at 6. So I should play at 7. Let's see. So I played at 7 and player 0 wins. Player 0 was AI. So to start, restart, we can press C again and we can play another game. Let's play 2 more games against AI and see if we can win or not. So let's start with 3 and let's see where it goes. Well, there is a very good chance of me forking, so I won. Let's play a final game. So let's start with five. Let's play seven. Hmm. I think it is a draw. So I played it perfectly. So that was all about the demonstration.
Future directions for TikTok AI systems. There is some limitations of these projects. Basic AI. The current AI follows a predefined set of rules and is unable to adapt or learn from past games. It uses a simple strategy of winning and blocking and other basic tactics, making it predictable. So no difficulty levels. The AI operates at a simple difficulty level. There is no option for users to adjust the difficulty based on their skill level. Limited complexity. The AI's decisions making it constant to checking only the current world state. It does not simulate future moves or evaluate possible outcomes more than one step ahead. Limited game expansion. The system is designed for 3 grid only. Expanding the game to larger grids for difficult variations would require substantial code changes, more memory improvements. Advanced AI algorithms. One of the most significant improvements would be implemented algorithms like min-max, alpha, beta pruning. This algorithm simulate multiple moves ahead and enabling the AI to make smarter decisions by evaluating the possible game outcomes. Machine learning based AI. A more complex AI could be developed using learning techniques such as reinforcement learning, where AI learns the strategies by playing multiple games and adjusting its behavior based on results. Dynamic difficulty adjustment. Dynamic difficulty adjustment would allow the AI to change its difficulty based on the player's performance. For example, if a player wins multiple times, the AI would switches to a harder difficult automatically. Game mode expansions and new game such as multiplayer mode would be added. Another improvement would be adding against AI versus play versus AI mode will be difficult settings. So there are another two improvement strategy we can use. Problem faced memory constraints. The 805 is limited internal RAM. We know that. So which restricts the complexity of AI and the data structure used. As the game logic knows, the limitation become more problematic. AI complexity. Implementing a more sophisticated AI like min-max or alpha beta cloning could be the challenging due to the microcontrollers limiting process power and memory. Keypad input and synchronizing process. The current method of scanning the 4x4 keypad can be error prone, especially when rapid inputs are made, leading to synchronizing issues. Component interfacing. As the system becomes more complex with added features, the interfacing with LCD keypad may become more interactive and harder to manage the limited microcontroller. Future improvement, upgrade the hardware, real-time AI, network play, game variants, 3D TikTok, like that. So that's why we can implement the future direction for Tic Tac AI systems. Limitations, improvements, problem faced, and further future improvements.